Hey guys, welcome back to my foundations for computer architecture. Part of this foundational series is I'll also cover some hardware descriptive language programming. I'm going to be using VHDL as that's what I'm comfortable with and what I used, but most of these concepts can apply to other programming languages like Verilog, and I'd recommend to look into other languages like Verilog. Now, first, before you do any VHDL programming, if you're using an editor like VS Code, I'd recommend installing an extension like Modern VHDL or VHDL. This just provides much more like static syntax error, like debugging. A lot of it is very helpful. It also color codes things, makes it just a lot more readable compared to just like black and white. Now, there are three different types of VHDL. You have structural, dataflow, and behavioral. I'm going to go over each at a time, starting from structural. Now, for structural, you can think of this as defining your most basic components and then building bigger, more complicated components using those smaller components. So this is kind of how you're going to be thinking about it as you're building any kind of computer hardware components in general. Um, but this is the hardware descriptive language way of doing things like that. So I have a couple logic gates laid out from the previous video. So this is an AND gate. Now, this is the lowest level VHDL, so it's just A and B, and then its output to Y. And it's the same for all the different gates, is that these behaviors are defined here. You can see XOR. It's exactly how you'd expect. Now, going back to the AND gate for an example, for VHDL specifically, there's a couple different points on the code. You first can look at your library usages. Obviously, you're usually going to end up using the IEEE package, sometimes standard logic, logic vector, numeric stud, all those different kinds. Now, at the start, you define your entity. This is when you compile this file, it'll create this um, entity, aka construct. So this is kind of like a prototype definition where you're just defining the ports and or like generics, aka those are like your constants. So if you need like specific variable or a variable width, you can have like define an 8-bit width. But from this, it just takes in 1 bit A, 1 bit B, and it outputs Y. And then you can see down here, this is where it's architecture, and then whatever word you want to use. I'd hope that you'd use something descriptive of what it is, and then of your entity is, and then you can define intermediate signal. You know, you can define an intermediate signal. You don't need it. I wouldn't recommend it. Okay, this is annoying. I don't want this. Um, you can define like signals that are inside your component but don't necessarily have a port in or out of your component. You can think of it as like a box, and you have your inputs and your outputs, and then this just defines what the like logic is. So that's it for the basic gate. So we're going to jump in. I have a full adder for each of the different types. So this is structural. You can see, just like before, you define your basic entity, you define your inputs and outputs, and then you have your architecture, structural. So this is a structural implementation of your full adder, structural, is. And then before the begin, you might notice that, hey, we just defined the components that we were looking at before that we have up here, like our AND gate, our OR gate, and our XOR gate. And you can see that the port definitions are the same. This allows VHDL to compile this file anytime in any order in reference to these other files. You can't run it without compiling all of the files, but it effectively works as a stopgap so that if you're missing your object file, it doesn't fail to compile this, even though you have all your files, just because it compiled it in a different order. Now you can see here that we defined our internal signals. So these are used internally and are not accessible to outside components. Now, if you're using some kind of waveform generator, you can usually see these internal signals depending on your debug settings, and it's very helpful to be able to see these. Now you can see you define, this is your object name. So we have XOR 1, our first XOR gate, XOR 2, our second XOR gate. We have our 3 AND gates, and then you can see it's this, a colon, and then your gate name or your object name. So if we look at our XOR gate, that is the same as this. And that's because when you compile this, this gets put to an object file that gets called on when you actually run the full program. And then you do port map, and then you connect your ports to either your inputs, outputs, or intermediate signals. So this is an input for a full adder. This is also an input for a full adder, but this is an internal signal. And you can see this is A XOR B, and then XOR'd with the carry in. So this gets put into this, which gets XOR'd with this. And I recommend to draw this as like, I'd recommend if you're programming any kind of hardware, you should always draw your schematic first. It'll make a lot more sense. And you can look up what a full adder looks like. It's basically a couple XOR gates and AND gates. It's not anything too crazy, but if you're confused on why this goes into here, which goes into here, and then, you know, your sum is used elsewhere, I'd recommend to look it up. Like look up a basic diagram of what a full adder looks like. But you can see here, we're defining all of the gates, we're generating all the gates, and then we connect our signals kind of like we're manually wiring it together. Structural can be the most intuitive hardware descriptive language. One important thing to mention is like when you run this in simulation, all of these happen simultaneously. This is not run as a sequence like most programming language you might have programmed in before, like Python or C or JavaScript, whatever. This all runs simultaneously. And you'll find that most VHDL constructs run like that, but there is a very specific exception to that running in parallel rule. The next example I have is dataflow, which, as described before, is kind of like, this is the lowest level. This is dataflow. And you can see that it has the exact same logic as your structural, but you don't have to define your subcomponents because you are effectively just assigning your sum to A XOR B XOR C in, and your C out is A and B or C in and A XOR B. Now you could streamline this even more. You could streamline this even more by having intermediate signals that go A and B and then go N, but that wouldn't streamline it in like a speed way, but more of a, you might understand it a little bit better if you see these come together and build into one. But this is you can see this is very concise. This is only 26 lines with comments, you know, and this is 64, and it's just a full adder. So structural can get very verbose, but dataflow can too. Don't let this deceive you. And you can see it's just a basic, you have your basic operand, your basic Boolean operands. You have other dataflow, like for example, if you use the numeric STD, and then you had a logic vector, which is basically an array of bits, you could use symbols like plus or multiply, just like you would in any other language. And it would instantiate the hardware required to do that, just like how it's instantiating the hardware to do these specifically. Like if you put it onto an FPGA board, for example. Um, and then the last example, and this one should be used with a lot of caution if you're in like an intro to computer, um, like computer architecture, computer hardware, hardware design in general. And that's because what I was talking about before, where everything runs in parallel, these two run in parallel, all of these structures run in parallel, but this is an exception. This is behavioral programming. This runs as a process, and this is your sensitivity list, um, which can be seen here as a basic rundown of the sensitivity list. Basically, you should always put any of the inputs that you read, because if you were missing B or missing A, and let's say A or B or C and updated and it's not in the sensitivity list, this wouldn't update. And that can be a very frustrating bug to deal with, especially if you're doing basic computer architecture implementation, if you're implementing like a basic RISC-V processor or some basic like hardware. But process statements can get very helpful for certain cases, and the main one would be a clocked process. So when you have a register and you want to write on a clock edge, sometimes you want to read from a clock edge. Sometimes you want to reset asynchronously, sometimes you want to reset on a clock edge. Using a process statement like this with a clock in your process statement, you can effectively guarantee that you only update on that updated clock cycle. This is a combinational process statement, which should be used with caution, because this does not run in parallel like the other ones. This one runs sequentially, so it starts up here and it goes line by line, and it this might seem more comfortable at first because it looks like C, and like a large amount of large language models love to use behavioral. I see it a lot where it'll spit out a bunch of behavioral, and while it's great because it can be concise, this isn't a concise example. Um, it can cause some really, really insane bugs if you aren't careful. Mostly from latching behavior again, like if your sensitivity list isn't updated right, or if you are missing this else, you might end up just getting stuck on some random thing and then everything's wrong and you can't figure it out. But behavioral is the third type of VHDL programming style that I'll be covering. And again, it's very similar to the other ones. Architecture, your word, this could be any word, but don't just name it something very random. You should have it be descriptive of what it is. And then your entity name, begin, and then you have your process, your sensitivity list, begin, and then you have your logic. And this is all run sequentially inside the process statement. All right, that's all. Good luck and have fun.